So with right triangle similarity, we want to know what relationships are formed when the altitude from a right triangle of a triangle is drawn. Well, what is an altitude? An altitude is a perpendicular segment from the vertex of the opposite side or to the line containing the opposite side. All right, so let's see, a vertex. So if we have a right triangle, so I have a vertex right here. And then let me go ahead and finish up my right triangle. And then what it's telling me is a perpendicular segment. So perpendicular segment right here. I drew a segment perpendicular from the vertex to the opposite side, or to the line containing the opposite side. So that is an altitude right here. This would be an altitude in a right triangle. So, and let's see here. So we want to be able to complete the steps to prove the Pythagorean theorem using similar triangles, and we want to identify similar right triangles formed by an altitude and write a similarity statement, and then apply theorems to solve problems involving geometric means. And geometric means is going to be a relationship using this altitude. And then apply the Pythagorean theorem to find side lengths of a right triangle. So again, hypotenuse, goodness, that is the longest side of a right triangle. That is the side that is opposite the right angle. And then the leg would be the other two sides of the triangle. So just some basic definitions and words that we want to be able to work with. So again, we have a right triangle, and of course the interior angle, we have a right angle, which is 90 degrees, and then we know the other two angles added together will be 90 degrees. And again, we have our hypotenuse, the side opposite of the right angle. Then we have our legs, and then the altitude is going to be that line segment drawn from the vertex. Again, I know this seems like a repeat, but hey, let's make sure we understand. Altitude, that altitude is drawn from the vertex and is perpendicular to the opposite side. Okay, perpendicular. Didn't mean to do that, meant to do this. Okay, and then, understanding that and knowing here that the right triangle altitude theorem tells me, let's go ahead and label some points. Okay, so we have identified here, I've gone ahead and labeled A, B, C, and D. And if I were to sort of separate those triangles, it may look something like this. Not exactly drawn to scale, but we can get the general idea here. This was a 90 degree, this was a 90 degree. And then we had point A, B, point D, and C. Hopefully you can see that I've sort of pulled those two triangles apart. And then the altitude is drawn, we create two similar triangles here. And they are similar to the original triangle and to each other. And then to prove that these two new triangles are similar to the original triangle, we can use the angle-angle triangle similarity criteria. So what I've done is I've just sort of copied that original triangle over here and moved it just where my orientation was a little bit different to make it easier to see. And let me go ahead and relabel that. I think it was BDA. So now if the altitude is drawn to the hypotenuse of a right triangle, which is what we did up here, then the two triangles formed are similar to the original triangle and to each other. So what we have here is we're going to have the original triangle ABC is going to be similar to triangle DAC. Right here, this is triangle DAC. And ABC is also going to be similar to triangle DBA, which is right here, triangle DBA. So then we know then that if ABC is similar to DAC, if ABC is similar to DBA, then we know that triangle DAC is going to be similar to triangle DBA. Okay, so that's my right triangle altitude theorem, showing my similarity. So as we look at the geometric mean, now the geometric mean of two positive numbers is the positive number x, blah, blah, blah. Geometric mean, let's look at that algebraically. A over x equals x over b. And what that means is we have this geometric mean of two positive numbers, a and b, is the positive number x that satisfies this ratio or proportion. Okay, so what does that mean if we look over here at our image? What is that going to tell us? Well, we're going to say that segment AD, segment AD over segment CD is going to be segment CD over, BD. Okay, so let's look at segment CD here. Segment CD right here is going to be the geometric mean between AD and BD. Okay, so this altitude is the geometric mean between the two segments that it creates, segment AD and segment BD. So geometric mean, my altitude. So when I go to look at that, so I have here that my height, my altitude is going to be the geometric mean between x and y, those two segments. So when I put some math in there, let's see if we say that x is equal to 2 and my y is going to be equal to 6. Well, if I do some substitution, x is equal to 2 over my height, and then my height over my y, which is 6. If I cross multiply, remember cross multiply, x times x, h times h, 2 times 6. So I end up with h squared equals 12, or finding the square root of h squared equals the square root of 12. H is going to be equal to the square root, simplifying this, 4 times 3. So that is h is going to be equal to 2 times the square root of 3. So that's the height of h, or the length of h, which is your height, is going to be 2 square root of 3 units. So using the geometric mean is simply going to end up being a cross multiplication and then simplifying. So when we do this, so looking at this example, we have triangle WXZ, and they are asking me, what is the value of A? Well, the value of A is going to be this little segment right here. And looking at my altitude, I have an altitude here drawn, and I guess I better give an end segment, right? So WY is going to be my altitude, so I should be able to identify here that WY is the geometric mean between ZY and XY. So ZY is 3, my geometric mean is 4, doing some substitution here, and then XY is a, so that would allow me to solve for a. So I end up doing some cross multiplying, and I have 3 times a is equal to 4 times 4, or 3a is equal to 16. Divide both sides by 3, and a is going to be equal to, well, 16 over 3, or if I were to simplify that, that would be 5 1/3 units. Okay, that's using my geometric mean to solve for missing variables. So as I look at this next example, I want to find out, I have triangle MNR, and I want to figure out what is the value of y. Well, the y isn't involved in my geometric mean, so in this case I need to remember that we do have a right triangle similarity with our altitude, so we should be able to say that I do believe triangle NRM is going to be similar to triangle similar to triangle NSR. So if I were to try to redraw them, so as I redraw them, what I've done is I've just taken, here's my original right triangle, and then I've taken the small portion, the similar triangle that was created when I dropped my altitude, and I've relabeled them, you know, just remembering that here the hypotenuse was 8, it was 6 plus 2, which gave me 8. This leg was originally the value of y, and then when I remove this similar triangle, again, my altitude was z, so my height here on this leg is z, my length on this leg was 6, and then my hypotenuse for this triangle was going to be y. So now I'm able to look at this as a similar triangle, and I should know that similarity, right? So I have, if I were to say that the ratio of 8 over y is equal to the ratio of y over 6. So similar, this side over this side is equal to this side over this side. Similar triangles, those ratios. So now I'm able to solve for an unknown value based on that similarity. So if I go ahead and do my cross product, I will have y squared equals 48. And then in order to find y, I find the square root. To find the square root of one side, I must find the square root of the other. So y is going to be equal to the square root of 16 times 3, or y is equal to 4 times the square root of 3. And that's, of course, units, and that is using that similarity property from earlier. So we were able in this to use similarity and also use my geometric mean property to solve for some unknown values. Again, being able to just move the triangles around, see their orientation helps immensely. Breaking them apart, don't look at them and just say, I think I can do this in my head. I was able to move them and identify them and make it easier for me to work out the problem. Oh. And then finally, let's go ahead and look at one last example, and we're going to say that we're given a right triangle. And, you know, the one thing that we haven't really talked about is the Pythagorean Theorem. And dealing with right triangles, that is going to lend a lot of benefit to working with this triangle. So the Pythagorean Theorem, so I have what would appear to be my hypotenuse, which is AB, is going to be 17. This leg, AC, is going to be 8. And, well, what in the heck is BC going to be? And we need to remember that a Pythagorean theorem is going to be a squared plus b squared equals c squared. Well, in this case, remember that c is equal to the hypotenuse. B is going to be a leg, and A is going to be a leg. Of course, using a right triangle. So we can do some simplification here. We can just say that in this case, this would be segment AC squared plus segment BC squared is equal to segment AB squared, right? So here is A, B, and C. So doing the substitution, we have AC is going to be 8 squared plus, we'll call this X. I guess we can just call it B, right? Why don't we just call it B? B squared is equal to 17 squared. And doing the math, you know, we get, what, 64 not equals 2, but plus B squared is going to be equal to 17 squared. And, you know, I don't have a calculator on me, so we'll just go 17 times 17 is going to be a 9, 4, 11, 0, 7, 1, let's see here, 0, 7, 1, I think that's correct. Looking at 289, yeah, I knew that. 289, so we do our inverse operations. And we end up with B squared is equal to 5, 2, 2. So we end up doing the square root of B squared equals the square root of 225. So, oops, B is going to be equal to 15. Right there, square root of 225 is 15. So when I come back over here to this little problem, I know that this length is going to be 15. So there you go. That length segment BC is equal to 15 units. And that's using the right triangle, the Pythagorean theorem, geometric mean, some examples for us to be able to use. And so when dealing with right triangle similarity, you want to make sure that, you know, you've identified some items. We talked about the geometric mean by drawing that altitude. The altitude is going to be the geometric mean between the two segments that it's creating. And then, of course, being able to use the Pythagorean theorem and then understanding that the altitude is going to create two similar right triangles. So this similar triangle over here, this similar triangle right here, this triangle is similar to the larger triangle that we just created, and then it is also similar to this triangle over here. So just looking at some of the similarity and using these problems, you know, we were able to identify some unknown features, and just make sure that when you're doing this that you try to, you know, write the problem down, separate your triangles for visibility so you can see what pieces are actually similar to what. Try not to do it in your head. It's just a way to fail if we do that. So write it down. Everybody can do that first step. Write it down.